Foam fractionation. What is that? Well, actually, it is a treatment method for PFASs. Foam fractionation in itself is quite an old treatment method, but applying it to PFASs actually use the PFAS properties as an advantage to remove them from the water phase. And this is also why I have kept this video of the treatment method separate from the other treatment method I talked about before in Water Tank Chat 12. Short, why is foam fractionation so interesting for PFAS removal? Well, basically, you have a small waste stream with a very high concentration of PFAS substances. So the waste stream is small, which is something you always strive for in all treatments of water, to reduce the waste streams, which you in turn need to take care of. With that, let's have a look at the foam fractionation. What is the conditions for it? How can it be used? What are the drawbacks of this foam fractionation methods depending on what PFASs you want to remove? Let's get on with it. When discussing treatment of PFAS methods, and to be clear, non-polymeric PFASs, you normally come across the PFASs I have listed in this table. And earlier in Water Tank Chat 3, we talked about the PFHPA or perfluoroheptanoic acid with 7 carbon atoms. So from different articles and data in the literature, when we talk about foam fractionation, these are the PFASs I will touch on, and you will also have some data before treatment and after treatment. Foam fractionation is a chemical process in which hydrophobic molecules are preferentially separated from a liquid solution using rising columns of foam. Now, this was from Wikipedia, and I would like for you to focus on the word hydrophobic. If you remember from the Water Tank Chat 11, when I introduced PFAS compounds, we looked at the hydrophobic part of the PFAS molecule. That is the carbon chain with fluoride atoms. And I also discussed why it was called hydrophobic. It did not want to be in the water. So the hydrophobic part of the PFAS will make it very suitable for removing by foam fractionation. And just a note, foam fractionation has been used many years before the PFAS came along, or the PFAS problem, to remove proteins and clean water, for instance, from fish farms and so on. So again, foam fractionation is not something new or an innovative method just for PFAS. It's actually used long before, which actually benefits us now when we will apply this method for PFAS separation. So let's look at the reactor vessel. And in this first reactor vessel that I will show you, we are using a counter current mode. And what does that mean? Well, basically you have the processed water here, the gray arrow. The water comes in the reactor and is flowing downwards and out. So you have the treated water going out in the bottom of the reactor. At the same time the processed water comes in, you aerate the water, and the water bubbles will then meet the incoming water in a counter current phase. So water treated out in the bottom, and the water bubbles, hopefully with a lot of PFAS on them, will be collected at the top of the reactor. And you can run this reactor in a continuous mode, which means that you continuously feed and take out the treated water, and also in a batch mode, which means you fill up the reactor, you aerate the water for a certain time, stop the process, take out the treated water, and of course collect the foam. Semi-batch, I won't go into detail, but with some imagination, I think you can sort it out that it's somewhere in between continuous and batch. Now, this was the counter-current way of running the reactor. There is also, of course, the co-current way of running the reactor. And here, if we start with the process water in, that will come in the bottom of the vessel. And here you see it will meet the bubble. So the bubble and the water will follow each other up, and then the treated water will leave, and the bubble will be collected at top of the reactor vessel. But as you see here, co-current means that bubbles and water follow each other up, and then just to short repeat, counter-current, water meets the bubbles, the aeration, head on, face on, in a counter-current flow. We're now going to look at a counter-current operating reactor and on two separate ways of running the reactor, operations mode, so to speak. And the first mode we're going to look at is the enrichment mode. And what is that? Well, very simply, when you add your process water to be treated in the reactor, you add it below the water level of the reactor vessel. And as usual, it comes down, goes out in the bottom and meets the aeration in counter-current. And this is called enrichment mode. So now what is the stripping mode? Well, very simply, the process water is now going in the reactor above the water level in the reactor. This is called a stripping mode. But again, it goes downwards, meet the aeration upwards, and it comes out in the bottom cleaned, and again you collect the foam at top of the vessel. So two modes of operation, enrichment mode and stripping mode, that you can find in literature and how to run these type of foam fractionating reactors. The reactor, counter-current, water in, water out, and bubbles meeting the flow in the opposite direction. And now we are going to have a closer look at the aeration, how to introduce the bubbles, but also, of course, the flow that you process through the reactor. And again, the flow will, of course, the more flow, the faster flow, will decrease the retention time in the water volume and the time to remove the PFAS, of course. But also the bubble size, which also is important. The bigger bubble, the less surface for the hydrophobic part of the PFAS substances to stick to, smaller bubble size, much larger surface area for the PFAS to adhere to or stick to, and thus removing more PFAS. You have some different ways of introducing the air. One of the ways, which is very common, is that you have a recirculation pump in combination with a venturi. And here you see a sketch that I have taken from one of the articles. You have the reactor, you take water, which you're recirculating with a pump, and you suck air through the venturi and introduce it in the bottom of the reactor vessel here. So circulation pump and venturi that sucks in the air from outside, creating the bubbles. Also, you can use a separate blower, and then you have different, how should I say, nozzles or contraptions to introduce the air. Here you see what we call a sparger, and this is a ceramic pipe with a pore size which can be 5 or 10 microns. So here you get very fine bubbles, and here you see an example of a sparger I've used in not for PFAS removal, but actually for dosing carbon dioxide. But here you have very fine bubbles from this type of sparger. But again, you have to look at how big is the reactor vessel, if this is a, how should I say, a practical way of introducing the air. Then we have different type of diffusers. Here you have a coarse bubble diffuser, and here you also can see the size of the bubbles here and the finer size here on the fine bubble diffuser system. So I'm not going to give any advice on what instrument or what application to use for introducing the air, but there are several ways of doing this, and of course when you have your applications or your project, you probably need to test what works the best for you. The water matrix will play a part in how well you can separate your PFAS substances, but also if you have other treatment steps that you need to take consideration to, the water matrix will of course play a very important role on how successful you are. I have chosen 3 different types of water here. One leachate water, which is reference 4, and the reference you will find at the end of this video. I have a groundwater, I have a fresh water. Looking at the leachate, you have a very high organic content compared to groundwater and fresh water, and also a very high chloride content compared to the other 2 types of water matrices. And a note, of course, groundwater, very low organic content, which can be expected, compared to the fresh water, of course. The chloride content in this groundwater was a little bit elevated, but it's still very low compared to leachate water. In regard to chloride content, just a note for the brackish water side, which run you about 3,500 milligrams per liter, for example, the Baltic Sea. And if you have a salt water, that would be the Mediterranean, Atlantic, you will be running about 30,000 milligrams per liter. So the chloride, of course, has a very high impact on the TDS content of your water matrices. I have also listed some other parameters that you might want to take a look at on how it can vary between the different types of water. We'll not go in detail on these, but looking at a treatment method, the water matrices, what you're dealing with is the first starting point when you start worrying about or assessing what type of treatment should I be using to get a good water quality, depending on my discharge limits. Here you can see different types of PFAS substances and their name, and also the number of carbon atoms in the different PFASs. In these 4 columns, you will find analysis from a groundwater, some wastewaters, and here a minimum value and a maximum value measured at the leachate water treatment plant in one of the articles I've used to get these data. And the references, the articles, you will of course find at the end of this video. Here are several number of PFAS substances, but I just want to point out these 2, which I think you probably heard about. It's the PFOA and the PFAS, or the PFOA, perfluorooctanoic acid, or a PFAS, perfluorooctane sulfonic acid. And here you can see in the groundwater you have very high concentration, and in this case it's a groundwater that has been contaminated by firefighting foam from an airbase. Looking at the wastewater or coming in, you have relatively low PFAS concentration, and they are the lowest that I have found in the literature. I mean, in regard to different types of waters that has been contaminated. So wastewater is of course at the very low end where you can find PFASs. And for the leachate water, you can see it's notable concentration in this leachate water, and also the variations. How does foam fractionation remove PFAS? First, I think you need to state that it's very dependent on the water matrices from the beginning. Then we need to split the question in two parts. If we are not using surfactants, or if we are using surfactants. Those two situations is very important for how good the removal of the PFAS in the water is done. Looking at the first graph here and reference 4, you have on the x-axis the number of carbon atoms in the studied PFAS. On the y-axis you have removal efficiency. And here you can see the PFAS with 6 carbon atoms, 7, 8, 9 carbon atom is removed quite well with foam fractionation. However, this is not the case for the PFAS with 3, 4, 5 carbon atoms. However, if you now look at the other graph on the right hand side here, and that is from reference 10, here you have used different types of surfactants to interwork or work together with the hydrophilic group on the PFAS substances. So you have non-ionic, cationic, zwitterionic and anionic surfactants. And again, if you remember water tank chat 11, I discussed the different type of PFAS and what non-ionic and cat, zwitter and anionic was. Now in this table on top here, I have added the number of carbon atoms for the PFAS substances to make it simpler for you to understand the graph. And looking at 4 carbon atoms, which we know if we wouldn't have a surfactant would be rather hard to remove. But in this case, using a cationic surfactant, we have a very good removal. So here we have focused the surfactant on the PFAS we want to remove. And this is something you will find out in pilot trials or lab trials, of course. And going up to another carbon chain, PFBS, you see here we have good results with cationic, also zwitterionic surfactants. So here you can actually get rid of the PFBA and PFBS using surfactants. And going off to 6, 8 carbon atoms to the PFO and PFAS, you see the longer the chain, the more of the surfactants works, quote unquote. But surfactant has a very good impact, mostly I would say on the shorter chain PFAS, is based on what I've seen in the literature I have looked at. I have picked out or tried to summarize some of the operating parameters for the foam fractionators. And airflow, if you have an increased airflow, you tend to get a better separation, but in return you get a higher volume of foam where you have less concentration of PFAS, which means that you have more of a waste stream. That means more to take care of. So increased airflow needs to be matched against the waste stream and the concentration of PFAS. And pilot trial, lab trial to see what is the optimum airflow for your water or water matrix. The retention time in a plant foam fractionator would probably range between 20 to 60 minutes. If I were to set up a pilot trial, I would probably go for looking at probably 30 minutes and then maybe 60 minutes to compare. Bubble size, I would say quite clear. Smaller bubbles, more surface area for the PFAS to be removed from. So fine bubble would give you a better separation. And how you introduce the air into the system, you have different options as I talked about before. And there you need to balance what type of equipment you should use, maybe depending on the corrosiveness of the water you're working with. But again, finer bubble gives you a better separation of the PFAS substances. Water temperature. Well, short chain PFAS is less than 6 carbons. I would say from what I've read, will be affected by a decrease in water temperature, not so much the longer chains PFAS. And again, a low water temperature decreases the reaction rate. This is, of course, quite well known. Surfactants or addition of surfactants, all depending on your matrix. Probably if you're looking at removing PFAS or PFOA, you don't need to use surfactants, maybe depending on the water matrix. But if you're looking at the shorter chain PFASs, probably you need to look at a surfactant that will help you remove the PFASs from your water. The overall goal in removing PFAS is, of course, to get a very good removal with a very, very minute waste stream to take care of. That waste stream which you have the PFAS substances contained in, you need to take care of, and you need to destruct the PFAS to get them out of the system as a whole. I will not go into different methods of doing this, but I just want to underline how important this step is, and there are methods for it that you can find in the literature. If you only have problem with PFAS substances, it might be that after the correct pre-treatment you can use foam fractionation as a standalone method. Also, of course, you can use the foam fractionation to remove PFAS before a consecutive treatment step. That could be activated carbon, ion exchange, or membrane filtration. Also, and this is also quite interesting depending on what type of water you're working with, but say that you use membrane filtration for your overall treatment method for your water. Then if you have PFAS in your raw water that you treated with membrane filtration, then probably foam fractionation will be quite interesting to use to clean up the reject from the membrane filtration. And I mentioned in the water tank chat 12 that the reject from the membrane filtration project can range between 10 to 50% of the feed flow, so to speak. But overall, foam fractionation can be used in many different types of application, and it's a quite interesting treatment method for PFAS. I will now in a short while show you the references, the articles I used to make this video, and I can highly recommend them. They are recent and they are very good. Probably when you read them through, if you are just having an interest for the PFAS subject or if you're working on a project, I think they will answer many of the questions that you have. They certainly gave me a very good introduction to the removal technique of foam fractionation. With that, I will now put on the references and wish you all well. Take good care and hopefully see you soon. Bye bye.